In this video, we'll discuss what Dkim, commonly pronounced Dkim, does, and why you should consider using it. We'll go over how it works at an overview level, and we'll look at how Dkim can be used in Roaring Penguin's Can It. If you're interested in the nuts and bolts, at the end of the video, we'll get into Dkim at a deeper, more technical level. First, let's see what Dkim stands for. Domain Keys Identified Mail. To help this acronym make sense, think of it this way. Outbound mail sent from a domain is signed using a cryptographic key which identifies that the mail really came from that domain and is not from a spoofed sender or has had the content altered. In other words, Dkim improves deliverability of a domain's email by letting the recipient check its signature and trust the origin of its messages. Note that this is no guarantee that the message isn't unsolicited commercial email or even spam or malware. So, how does it work? Once email is sent, the email is signed as it passes through a mail server on its way out from the sender's domain. The server that signs it could be a machine that the sender's organization controls, such as their own mail server, or it could be a service that they trust to handle their outbound email, such as a third-party service like Can It. The Dkim signature promises that the message contents a recipient gets are the same as what the sender sent, and as we'll see in the next slide, that it really did originate from the sender's domain and wasn't spoofed. So, this Dkim signature is added to the email as a new message header, and delivery continues as normal. At the recipient's end, a Dkim signature is only useful if they check Dkim. If the incoming email has a Dkim signature, then the recipient server looks up the public key from the sender domain's DNS record. This key is used to verify that the message contents match the Dkim signature. If it passes, then the recipient knows that the message it received is not altered from what was sent. Since the public key came from the domain's DNS record, the recipient can trust that the message really did come from that domain, as opposed to it being a spam where the sender address is spoofed. Now, let's discuss some downsides. Lack of a Dkim signature in general means nothing. Most organizations don't use Dkim, so a general rule to block or punish messages with no Dkim signature would be terrible. Let's say somebody's desktop computer was infected by a virus that caused it to send tons of spam. The messages would go out from the desktop through the organization's mail server, where they would be properly signed on the way out. So, a general rule to approve messages that pass Dkim is no good either. Consider another case. A spammer could set up a fake domain that looks very close to someone's real domain. Then they could send tons of properly signed spam, which only an observant recipient would spot. In summary, any general case rules can have unintended consequences, but rules for domains you trust can be useful for improving deliverability. Roaring Penguin's Can It service lets you make use of Dkim in two different ways. While filtering your inbound email, you can make rules for Can It to check Dkim on domains you trust, approving mail that passes or denying mail that fails. If you use Can It for your outbound mail, you can configure Can It to sign your mail with Dkim signatures. One of the roadblocks preventing organizations from using Dkim to improve their mail deliverability is the technical challenge of making their outbound mail servers use Dkim. Our service makes the technical setup very easy to complete. We create a key pair and sign your outbound email as it passes through our filtering servers. All you need to do is publish the public key in a DNS record, which we provide for you. To summarize, Dkim checking on the inbound side can be useful in receiving email from domains that you trust. General rules that apply to all domains are not recommended, but you can use rules for specific domains to help ensure deliverability. Dkim signing on the outbound side can improve the deliverability of your outbound mail. Many organizations, including major organizations like Gmail and Yahoo, use Dkim. Roaring Penguin's Canet filtering service provides both inbound Dkim checking and outbound Dkim signing. And in particular, Canet simplifies configuring Dkim signing for your outbound mail. The Dkim overview portion of this video is finished. In the next few slides, we'll take a more technical look at how Dkim works. Here, we see an example Dkim signature that I captured from a test message. Understanding the various parts of the signature will help us understand how Dkim works. The version tag is there so that Dkim will be backwards compatible in the future. There is a selection of algorithms for making signatures. The algorithm tag lets the Dkim checker know which to use. Canonicalization is important because it's possible for some mail servers to make changes to a message while it's in transit, such as adding extra line space or changing a message's headers with different capitalization and spacing. Dkim includes a few options for how tolerant to be about these changes. The domain tag tells the checker which domain the mail is from. As a message passes through servers on its way to its destination, new message headers will be added, and some can be removed or changed. The Dkim signature should include some headers, such as the from, to, and subject, but not all. The header tag lists which headers are included. It's possible for a domain to use several different keys. For example, messages from technical support could be signed with a different key than those from sales, or a domain might switch to a new key. The selector tag specifies which public key the checker should use. Decrypting a signature takes quite a bit of computing time. However, hash functions can be computed quickly. We'll discuss what these are in detail in a moment. The BH tag contains a hash sum of the message body, so that the Dkim checker can quickly see if the contents are okay before continuing with the relatively slow process of decrypting the signature for the full check. Finally, the B tag contains the signature. Both the message body and the select headers seen in the H tag are included in the signature. Here we see the DNS record for the public key that matches the private key which was used to create the Dkim signature we just saw. Notice the name of this DNS entry is main._domain key followed by the domain. This is the format Dkim requires. The main part is the selector we saw in the earlier signature. Optional information can be included as flags, which are specified in the T tag. The Y flag here means this domain is testing Dkim. The K tag specifies the algorithm used for the public key, and the P tag is the public key itself. To understand what a hash sum is and the difference between encrypting something and signing it, we start with a question. How do I guarantee that the data you receive is the same as what I sent, that it didn't get changed in transit? Well, I could encrypt it with a key pair. What's a key pair, you ask? There's a clever way to use randomly generated data to create a pair of keys, such that anything encrypted with one key can only be decrypted using the other key. If I encrypt some data with my private key, and I make the other key public, then anyone can decrypt and read the data, but nobody could modify it. They would need my private key to encrypt their own modified copy, or else they could just make random changes to the encrypted data, but then the recipient would just get undecryptable garbage. However, encrypting the message itself is no good, because the recipient will need both the public key and some software to be able to decrypt it, or else all they have is unreadable encrypted data. I want you to be able to read my message even if you don't have decryption capability, so I don't want to encrypt my message itself. We'll talk about hash sums in the next slide, But for now, if I feed my message data into a hash function, I get a hash sum. A signature doesn't encrypt the data itself, it encrypts the hash sum of that data. So when you get my message, if you A, make a hash sum of your copy, and then B, you decrypt my signature using my public key to get the hash sum that I encrypted with my private key, well then, if A matches B, you know you have an unmodified copy of the data I sent. A hash sum is the result of a one-way mathematical function. We call the mathematical algorithm itself a hash function, and when you put data into the function, what comes out is a hash sum. In this example, I took the text, "This is hash summed," and fed it into the SHA-1 hash function to generate a SHA-1 sum. If you use the same algorithm on the same data, you'll always get the same result. Hash functions are very clever in that there is no way to look at the output and figure out what data was used to generate it. It's one way only. There is also no way to figure out what other data could be fed into the function to generate the same output. So, hash sums are one way and irreproducible. Unrelated to Dkim, a slightly more complicated version of hash sums is used to store passwords, so that if anyone ever gets hold of the hash sums, they can't figure out what the original password was, or figure out something else to use in its place. Hash sums are very fast to calculate, which is why the Dkim signature includes the unencrypted hash sum of the data in the BH tag. A Dkim checker can quickly see if the data is okay before spending more time decrypting the signature to do a full check, and thus can avoid some types of denial of service attack. Finally, hash sums are a fixed size. No matter how much data is fed into the function, the output is always the same length. So, whether your email is a short greeting or several megabytes of pictures, the signature will always be short, and so the addition of a Dkim signature won't make a significant difference in the size of the message. That wraps up this video. I hope we have helped you understand Dkim. Thank you for watching.